Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And welcome to the session on big data. We've had a slight change in the schedule. Originally, we had 3 speakers scheduled. One had a family conflict, scheduling conflict, so we're down to 2. But fear not, these are 2 really great speakers on some great topics. The 2 speakers we'll be speaking today, the first speaker, Pat Helland from Microsoft, currently working in our online services division, will be telling you about the big data challenges we face in Cosmos, which is the back end for Bing that serves up the index, builds the index, analyzes the data, and it truly is one of the big data challenges and groups that we have inside of our company. Our second speaker in this section is Szalay. We'll be telling you about some of the work he's been doing on Petabyte-Scale science, and he's actually been taking on some of the biggest challenges on science data management over the last decade. And we'll have some very interesting work to tell you about in his session as well. We are going to try to take the full time we have here today for these speakers to present the work, because we know you have the lunch, the breaks, the cruise tonight to talk to them and discuss this work further. But if you do have a question that comes up while they're making their presentations, I would encourage you to go ahead and raise your hand if it's a clarifying question and ask it during their talk. And they'll make good use of the time or push the question off to the end if they have to. So please, with no further ado, Pat Helland.
Thank you, Roger. Yep. So my name is Pat Helland. I've been doing scalable big stuff for about 32 years. I super remember the big debate of whether we would get to 1,000 transactions a second. That was a huge concern in '85 after I've been doing it for a while. And so let's see if I can get my slides up here. And so I've been working for a couple of years on this project called Cosmos. And I'd like to talk about big data and big challenges and tell you what this crazy thing is. What I want to walk through is an introduction, then an overview of Cosmos and what this product is. And when I say product, we use it internally. It's an internal service. It's not available to the public. It's supporting Bing. It's supporting all of the online services division, Bing, the ads, MSN, things of that nature, a few other things inside of Microsoft. And so this is stuff we're doing internally, right? What is Cosmos? I want to tell you about a change we did over the last year or so called structured streams, and then go into a few other exciting projects and conclude. So what is Cosmos? It is a petabyte store and computation system. We have about 62 physical petabytes stored, and which represents 275 logical petabytes stored. It turns out that the compression more than makes up for the triple redundant storage that you have. And a friend of mine loves to talk about a couple of exabits, right? You've got to get that exa in there, right? You know, and it's fair, that is. And there are tens of thousands of computers across many data centers. This is massively parallel processing based on Dryad. Now, Dryad is similar to MapReduce. We think it's cooler. It's got some features. It's a better way of doing it. But it's, this is how we do it is with Dryad. And so you set up directed acyclic graphs, and you send work out here and data out there, and then it computes, and then you hook this stuff up, and you get the computations. And there's automatic computation placement with data. It is hard, even in a data center, to get a flat network. I'm not saying we can't do it, won't do it, ever, all that kind of stuff. But when you are dealing with a non-heterogeneous, with a heterogeneous, non-homogeneous network, it becomes advantageous to put the computation close to the data so that you aren't squirting too much crap back and forth across a precious resource called your intra-data center network. So SCOPE stands for Structured Computation Optimized for Parallel Execution. It is a language, a compiler, and an optimizer. It's a SQL-like language that offers set-oriented record and column manipulation. And so you point it at very large data sets, you churn and churn and churn, and then you generate potentially very large data sets. Okay? And SCOPE does that, and it is automatically compiled and optimized for execution over Dryad. And finally, we have management of hundreds of virtual clusters for computation and storage allocation. So Microsoft's a big company. OSD is a big division. Who the heck gets to use these things, right? Well, it turns out I don't want to be making those decisions, and our team doesn't want to be making those decisions. So the virtual cluster mechanism is a way for folks at a higher pay grade to decide who gets how big of the pie, and then we implement how that work is allocated according to that stuff that they have allocated to our customers. So the way to think about it is that if you want to work with Cosmos and you're a department inside OSD or another part of Microsoft, you buy machines and give them to Cosmos. Well, in reality, you let Cosmos buy the machines because we're not just going to take the ones that you want. They got to be our flavor, okay? And then we guarantee you get compute resources proportional to the amount you've contributed. And we also let people use those compute resources when somebody's not as aggressively using them up, okay? The key here, and I'm going to reinforce this, is having ubiquitous access to all of our data is turning out to be the business driver for many, many things. So non-siloing is huge, right? People are always surprising us. I mean, everyone continues to get surprised by, oh, if I look at this data and I compare it with that data and I learn this stuff, then we can make more money. Well, that's fine if it's all in Cosmos or in something like Cosmos. It's a disaster if you have to figure out how to talk to that set of computers over there with some proprietary protocol and you can't just go and slice and dice with some high-level language, okay? So that is a driving force behind big data, which is just fascinating as time goes on. It's big business means big data in many cases. So Cosmos and OSD computation. A couple of weeks after I joined the division, I said, this is how I understand it, and I drew this picture, okay? And nobody injured me. They actually said, yeah, you're right, we didn't think of it that way, okay? Well, it turns out that what OSD does is it gets data coming in from the internet, and it gets other data from feeds from merchants who want to sell stuff, and you name it, right? Stuff comes in from the left. And now on the right-hand side, there's all these people who are searching and doing MSN and all this kind of stuff. You know, requests go in from the right-hand side. Stuff from the left, requests from the right. Now, there's a set of front-end computation that is servicing the human beings that are talking, right? Search indexing, you know, so that you come in, you get your answer. How do we feed the ads? How do we do MSN? All that stuff is designed around human interaction. And as it's working, it's logging and recording and saying, oh, I did this. Oh, I saw that. This is what's happened. So there's huge volumes of user and system data that are being generated. So that data from the front-end stuff is going back into Cosmos. It's being stored in the batch back-end system for analysis, right? And what you have in the back-end system are large read-only data sets. And you crunch them, and you think about them. And then the results of that go into the front-end online system and influence what the users will see. Maybe after a while, but it's how the system works, is with this big loop and this big circle. Now, Cosmos provides storage and computation for that batch back-end data analysis. It doesn't really today support front-end stuff, but we're in many discussions about what it would mean to have caching in the front end and stuff going into the back end, but that's where we're growing. Right now, this thing looks like this. Big batch back end, front end, users, big crunching. Cosmos is a service. Okay, I'm fortunate enough not to wear a pager, and mostly that's because I'm incompetent to help fix the damn thing, okay? Otherwise, I would be, right? But my buddies are all taking turns being DRI, designated responsible individual, which means you may get awakened, okay? And so what happens is this data drives search and advertising. We have web pages, search logs, IE logs, what did people visit, advertising logs, all that stuff is analyzed. And we generate about 2 petabytes a day, okay? And there's hundreds of petabytes of search UX, toolbar, searching is hundreds of terabytes. The web snapshots are many tens of petabytes, MSN, Hotmail. We compute and ingest a couple of petabytes a day. And that is, I think, more than Azure stores, but I could be wrong, okay? Cosmos is the back end for Bing analysis and relevance. Clickstream information is imported from many sources and cooked. Queries analyzing user context, click commands, and success are processed. So we showed you this. Are you happy with it? If you're not, how are we going to influence it so next time we show it, you're happier? Cosmos is a service. Our team runs the code on many tens of thousands of computers. Users simply feed in the data, submit jobs, and get their answers back. This kind of making sense as a framing for what Cosmos is. Okay. Now let's look briefly at the architecture. This is designed to go fast and to be very, high level. At the bottom, we have a store layer. The store layer has many extent nodes that store and compress and replicate extents on disks. So the extent node, these extents are identified by a GUID. They're kind of up to a couple of gigabytes, and we always triple replicate them. And if we see that there's only 2 replicas, it's really important. If we see there's only 1 replica, oh my God, it's important, okay? And issues that can happen when you have failures and whether you have replication storms and how do you manage that and how do you make sure this doesn't get screwed up are fascinating. Turns out we compress the data independently on the replicas, and so one may be more squished down than the other, but it doesn't really matter because you're getting the same bits out when you unsquish it. Okay? It also means you can kind of store it with a medium squishiness, and it's there, and then later on you can invest some computation in having it take less storage time. We always have to scrub disks. Okay? You cannot count on triple replication unless you go and look at it every once in a while, because the longer it takes before you look at it, the more likely it is you can't read it again, due to a phenomenon I call bit rot, right? You write something on disk and it may or may not be there when you go read it. And that works fine as long as you have 3 of them, as long as you keep looking at it, right? So we kind of read the disk, try to make sure every 3 or 4 days we get through the disk, and make sure we've read everything at least once, and every once in a while, oh crap, and then you go and you make another replica out of the 2 you already had. Is that making sense to everybody? Okay. On top of the extents, we have a notion called a stream. So we have a really straightforward, simple directory that we have. Got a name of a stream. A stream is a sequence of bytes comprised of a set of variable length extents. Okay? So this is, it's great technology. Other people have done similar technology. We have an execution layer. And by the way, you have a big team that's got to deal with this, and there's just stuff. And we have another team that deals with the execution layer. Execution layer, jobs queue up in a virtual cluster. When the job starts, it gets a job manager process, which is trying to figure out, okay, how am I going to run this dryad directed acyclic graph, and how do I feed the data to it? Where the hell is the data? Oh, the data's over there in that part of the cluster. Shit, I better run the computation over there, close to where the data is, okay? And then I'm going to take its answers and try to keep it close. And now you've got this problem, which is, because I'm trying to do local placement of stuff, my queuing and my allocation of resources has got constraints. When do I do what allocation trade-off in there? And I will not claim we do it perfectly. I will claim we do pretty well, and that the better we do here, the more we can get out of our compute resources we purchased, right? And so you see many processing nodes, PNs, hosting the execution vertices, which have computation which takes data in and data out. This, of course, works because it's functional, data in and data out, and then they're producing the results. We have stages in the computation. We have challenges with outliers. Okay, so if I've got 1,000, vertices in the stage, and 999 of them are done, and one of them's taken its pokey old little time, that's hard to explain to the customer why the heck their job took so darn long. Okay, and that's interesting when you have customers who need their answer within a particular window of time in order to satisfy a business commitment with one of our partners. And so that's part of the fun of working in this area. And it is fun. And then we have the scope layer. So scope code is submitted to the scope compiler, doing these set-oriented expressions. The optimizer makes decisions about the execution plan and the parallelism, and it generates an algebra which describes, okay, I'm going to take this, and I'm going to feed it to this, and I'm going to run it, and it creates that directed acyclic graph logically, and hands it and produces it in a way that the JM and the execution engine can process it to get stuff done. Okay? So this is a real, living, breathing, important business system. Let's look deeper at the store layer. Store layer has 2 major components. There's more, but these are the biggies. The extent node implements a file system holding extents. Each extent is about 2 gigabytes max. They can be shorter, okay? Compression and fault detection are important parts of that. Now, it turns out we tend to buy the same computer over and over and over again, except for there's the new version, which is better this way and different that way and so forth. And so they tend to all have a certain amount of computation and a certain amount of storage, right? And the extent node consequently is running just about everywhere. So I have one on just about every machine and some disks on just about every machine, and it's responsible for managing those disks and then feeding it into the soup of this ginormous cluster. We have the CSM, the Cosmos Store Manager. Now this is a Paxos protected, highly available directory service that manages a slice of the namespace and manages awareness of the replication and the placement of the extents. Okay, and this, I think it's fascinating how things grow. I mean, I believe systems grow like cities, okay? And one of your worst punishments is to be successful, okay? And so we are still struggling, but doing fine and holding ourselves with our head above water with the fact that the amount of stuff we're storing means that we're actually having multiple volumes of the CSM. And things are sometimes coordinated and sometimes not, but making sure that all the customers are happy as we deal with scale and deal with scale with the directory and the coordination with the stuff. And so that's been quite a bit of fun, making it scale and manage the namespaces and so forth. And we dream about and are working on a project to make that much more automated. Execution engine, again, takes the plan for parallel execution for the scope job, finds computers to perform the work, places the data in the computation close to the data, makes sure all the inputs are available before firing it up, responsible for failures and restarts. Dryad is similar to MapReduce. So the execution layer logically runs first on top of computation resources, but also on top of streams. So it basically doesn't know a ton about extents. The only thing it does know about extents is that's the unit of data placement. And so the partitioning of the computation is frequently along the extent boundary because this extent might be there and that extent might be there. And so it's abstracting and understanding how the data is placed. Scope language, structured computation optimized for parallel execution. Again, heavily influenced by SQL. And we go back and forth, right? There's some folks who would love to have something that's more influenced by LINQ, and we think we should probably add that in. And that would be great and wonderful for the folks who are into the object-oriented application development environment. I totally support that. But there's also a class of people for whom the SQL-like expression, their business analysis is, and their business analysts, and for them it's much more approachable to have this class of expression. And so we definitely don't want to walk from this, even though we consider maybe identifying the equivalences, and we've had lots of discussions about the equivalent nature of the set-oriented expression. But anyway, when you deal with a scope job, I have a couple streams in this example, stream A and B, that are input. They were there before the job started. Run the job. If life is good, there's 3 new streams that are created as a response to completing that scope job, which may be 10 minutes, maybe 24 hours, depends upon what's going on. Sometimes they're very, very, very large computations. Scope is a high-level declarative language for data manipulation, and it does translate naturally into parallel computation. So the compiler and the optimizer take scope programs, create an algebra describing the computation, break the work down into processing units, the descriptions of the input and outputs for the processing units, and they make decisions about compiling and optimizing that are driven by data size and driven by minimizing data movements. That may change over time. If data movement becomes a less expensive artifact than it currently is, we have the latitude to adjust the optimizer. It depends on, these things move as you go generation to generation. The coefficients on your costs change. And because we're managing that, we can manage changes associated with that over time, transparent to the application. Finally, the virtual cluster, which is a management tool, right? And so it allocates resources across the group within OSD, each model captured in a queue of work with priority within the VC. The cluster has guaranteed capacity, and it will bump other things aside if someone's using its capacity, but you can also move in to use idle capacity of people who are not there working on it. Let's talk about structured streams. So this is something near and dear to me because I came and helped drive the high-level architecture for this, year and a half or so. And it's running and, really helping things already. So Cosmos supports streams, and in hindsight, we renamed them unstructured streams. They were always just streams. Now they're unstructured streams because we have structured ones too. And you create those by appending and writing to the end of the stream. Structured streams are where scope writes down the metadata defining column structure of the data that's in it, and the affinity clustering information. And it turns out that it simplifies extractors and outputters. I'll talk about that in the next slide. And it offers performance improvements by having column features for processing optimizations, affinity management that can dramatically improve performance, and key-oriented features to be able to use indices to get down in there. Let's dig into that. I should have said not today's. Well, it is today's. If you have unstructured streams, it's today's. So when you use an unstructured stream, which was your only option up until recently, you had to write a piece of application code. Now, you might have picked up a standard one, right? But you had to come up with an extractor. The extractor looks through the records that are coming in, and it figures out the columns and the data, and it calls and says, yeah, I got this column and this data, and I got this column and that data, as you're parsing and taking apart the stream. Then in turn, when it's time to generate the output, you would call a piece of user code called outputter and say, here's the record I have with these columns in it, and then the outputter would generate comma-separated values or whatever it chose to do to write down the representation that it spit out in a stream. Okay? But the outputter discards the metadata as it's known to the system. Now, we have complemented that by the ability to actually have scope write out metadata and generate the stream in a way where it understands it. So not only is there a description of what the records in the columns look like, but there's a description of the key, there's ordering, there's indexing, there's partition boundary information, and there's partition placement with affinitization. So what does that mean? You can walk up and say, I want to spit that stream out, and I want to use it so it's similar to this one right over there. Well, this one's been spread in 50 chunks in various places in the network with this key range. So this key range is going to go close to him over there, and that key range is going to go close to him over there. Later on, when you want to join them or something like that, that computation can be placed right there in the network so that it's fast and you don't have to have much data movement. So streams, metadata, and increased performance. By adding metadata describing the stream into the stream, we can provide performance improvements of cluster key access and partitioning and infinity. The metadata is kept inside the structured stream. That turned out to be a very simple thing to do when you're generating immutable data. You're writing an output. This is the thing. Hey, if I pick it up and I move it over in this place in the directory, it still means what it did, right? And so I want to emphasize computation in big data is different than computation in a classic database. You write immutable artifacts and potentially version them, right? You don't have the current anything, right? It's a very challenging notion to have the current anything in a ginormous system like this. And so this works really well to just write down what it meant at the time you wrote it. You could do cluster key lookup. That makes a huge performance improvement. No surprise, this is a pretty classic database trick, but it's not a classic parallel computation trick, okay? Because in the parallel computation, you classically are going over all the data and sucking to calculate it. But if you only need a piece of the data, now we know we can get at it really easily and really quickly by looking it up, assuming you can get at it by the primary key and look up quickly to get there. And the way we implement partitioning and affinity is as we're running and as we're building the stream, we actually make a set of temporary streams and put the relevant data out there into temporary streams and then glom them together into one stream. And so what that means is even though it comes out looking like exactly one stream, and it is one stream, we've now placed these temporary streams at various corners of the cluster with affinitization, and it's actually all the replicas are affinitized with some stickiness in some nice ways. And so that actually allows us to then process them with a lot of performance improvements. So this has got some really nice things. Let's look at a case of aggregation. I'm going to take a sum as a total score from a web table grouped by domain, and I only want the top 100 domains that have this score. Well, what did I have to do in unstructured streams? I had to process over everything and do a table scan and a sort and a partial aggregation and a partition, and then I had to pull them back together into a full aggregation, and then there was all this stuff, and that was an expensive sort that occurred there, and that was a super expensive crossing everything with everything right there, and all I was doing was trying to get the top 100 by this score. Now, what I can do here is instead, I can do this without shuffling the data because, I'm sorry, I went too fast. Each of the partitions can actually go through and do their own, what are the top 100 in my partition, and then that's all I have to bring together because of the way we've organized it. In selection, right, if I want to find something where it's, the URL is equal to imdb.com, we used to have to go through the whole damn thing. We would read the whole damn data set and look for everything that had just stuff related to IMDb.com, because that's all you can do in many of these systems, and that's where we were, and that's where we've grown past. And instead, what we can do is look up the partition metadata and say, oh, that's in partition P100, and so then I go to P100, and even when I'm within the partition, I don't have to look at very much. Within the partition, I can use an index seek, and way the heck faster to do a selection, just jumping down to do that. So I can find it fast. And then if I'm joining multiple data sets, right, and I want to actually take where the URLs are equal from two different data sets, we used to have to do this, massive data read, massive sorts within the partitions, massive, super expensive, everybody's talking to everybody, and then you're making a merge sort. And instead what we do is we find the particular partition that's got the relevant URL, filter it down, and then only join on the subset of the data that's relevant, and it's hugely important. Now, you would say this is boring. Database guys, 30 years ago, whatever. Except applying it here, I don't know how much that's been done before. And all I know, by the way, is as a Microsoft stockholder, we're using a lot less computers because we did this, okay, to get the same answer. So maybe it's boring, but it's saving us a lot of computation. Am I worried that DeWitt's going to savage me? Dave DeWitt, I'm not worried about Dave DeWitt. I love Dave. But I'm not worried. Yes?
This is a big, giant shared disk system.
This is a related question. This is a big, giant shared disk system in some sense.
Storage is separated.
I understand you're arguing the storage is separated from the computation. Yes and no. I mean, it's different enough that I'm not sure the advantages of looking at the analogy are helpful in terms of understanding the system, but I also don't believe you're misunderstanding things when you say that. It's clearly not a shared nothing system. But then again, I want to point out, shared disk systems had their difficulty associated with concurrent update. And this is read-only generating a new version, and so everything about that just is thrown out the window. I can make as many copies as I want of the immutable data. It's just a different beast once you're doing functional calculation. And I'm fond of saying that I love functional calculation much more than dysfunctional calculation. And so, some other exciting projects. So we're working aggressively on reliable pub-sub processing, right? So we're going to do high-performance pub-sub event processing. When I say high performance, many, many tens of thousands of events per second, okay? I'm trying really hard not to tell you anything more precise, right? But big numbers, okay? Publications receive append-only events, right? Subscriptions define the binding of the event to code that will process every event. So I could have more than one subscription for the publication, which ends up being a wonderful thing as you try to compose systems. Very good software engineering tool. But I've got this thing, and it's receiving these events. And now we're going to sign up to have this piece of code that every event that comes out of there is going to be fed into that code and processed. And we'll look in the next few slides about what kinds of things you can do while you're doing that. But that compositional nature is super important, okay? And being able to do it with super scaling and amazing partitioning and custom managed pools of event processor with automatic load balancing because we have so friggin' much work going on, okay? And then the events are appended to those publications either by other event processors, so like the yellow thing can push something out and as he's doing his work, or outside of Cosmos, people dropping turds on Cosmos, okay? Now, we're building random access tables, okay? So a table is a set of records in which is a key value pair. Tables may be randomly read and updated. So this is a twist on the way data is represented as compared to scope. And pulling and unifying scope together with this has been a part of what I've been having fun with the last few months, and it's working great. We're figuring it out, how we can unify the batch computation and the random access computation. We're working to do very high performance event processing. Again, many tens of thousands per second for each kind and many kinds. And if you want more, just add computers, right? Honest. That's the idea. Just add computers if you want more. And the event processor, that user application code, may read and update records within tables, and it may append to a publication. So here, the perspective of this yellow event processor is, I just got woken up and told event X, and I have some app code, and I know what to do with a record that is an event like this. Okay, so that means I got to do this work on this data. Okay, so I'm going to go read this record out of this table and read this other record out of this table and do this computation and change that record in that table and change that other record in that table. And now I've done my step in the pipeline, and so, gee, I need the next step in the pipeline to get done, so I'm going to generate an outgoing event over in that publication, and then he'll do that work later on. Okay, and so there's a composability associated with that. I can have 0 or more outgoing events for every incoming event. I may make changes, I may just read only, whatever. But interestingly enough, we are working to make that have an atomic transaction boundary where for each subscription, the event in the publication will be processed exactly once. Okay? And I've been doing transactions since easy 82, if not before then. And I understand exactly once and how important that is and how that lowers the barrier to entry for the app developer, even though it carries a burden. And there's some interesting discussions because I've been on record as being a transaction lover and oh my God, go careful and watch out for the dragons if you touch transactions. And there's circumstances in which we can do this at large scale inside of our data centers. And so we're working to combine random and sequential processing. So random processing is event processor applications randomly reading and updating very large tables, and I mean very, very, very large tables, the kinds of numbers you've been hearing me say, right? With extremely large throughput. Also, applications external to Cosmos, running in whatever the heck they're running on, coming in with web services and reading and writing tables that we're holding inside of Cosmos. Transactions controlling atomic updates by the event processors. And that's essential that the effects of the event processor are atomically coupled with the incoming work demanding the work from the event processor so that you have a correct behavior. And then what we're doing is those changes are accumulated as deltas to the table, talking about the timestamp and talking about when the change occurred and when this thing committed. And then you create a set of deltas. And then as you read, it's our responsibility to read through those sets of deltas and give you the version that is consistent with the timestamp that you are examining. Okay? And within certain bounds, we can actually let you do going back in time a little bit. Why is that important? That's super important because I don't know what a batch job means unless I give you a consistent snapshot. So now we can then run a scope batch job against a time in the past, but not necessarily very long in the past, snapshot of the data which is concurrently being randomly updated. Now it turns out that the performance of random updates and the performance of sequential updates are sometimes at odds, and so we're working to build a system where we can control that and assign, you can build an app, and even at the time you program your application, you don't really know if it makes sense to break these into pieces, and do column structured type of stuff. Very, very similar to column-oriented databases, same motivations. The column-oriented database stuff is much the same as the sequential processing stuff if you squint at it right. And so those trade-offs are very important to us. And we haven't completely figured out how we're going to use SSD. We know that some of the proposals would fry it in about a day, and so those proposals aren't the ones we're going to use. But there's others that we think we really get a ton of value. So I'm just going to wrap up and be comfortable with our time. So Cosmos manages OSD's data and computation. We have hundreds of petabytes of data, many thousands of very large batch jobs, tens of thousands of servers in multiple data centers. All data in the same addressable store is essential to business. The money lies in mixing, matching, slicing, dicing, learning, and coming up with business value out of that data. And every time you put it in a silo, you have a pending problem for where you're not able to do what the business needs. Cosmos is evolving. It's constantly evolving. It's constantly growing. Structured streams combines large-scale parallelism with database techniques to dramatically improve the efficiency of the computation. Integrated random and sequential processing over the same data. Reliable workflow via pub/sub. Transactionally correct changes over many petabytes of data. We need talent. Send us your kids. We will teach them a lot and work their butts off. Okay? So, questions? Yes, Mike.
Who are some of your internal customers for the pub/sub stuff?
What are some of our internal customers for the PubSub stuff? Almost everybody doesn't want to wait a few hours for their answers, okay? And so it turns out there's many, many kinds of applications that are structured way best if you can let things flow through. Like, I always think of it as a big pachinko machine with the balls flopping around and things coming out. And interestingly enough, I think most of the customers over time will gravitate towards that. And the only times that people will really stick to the larger set-oriented stuff is when they're much, much more comfortable with waiting quite a while and gaining some of the efficiencies that can be gained by the concentrated set-oriented batch analysis. That make sense? It's fascinating, the interest and the demand for it. Yes. Hey, Hector.
Yes. So, as you mentioned, there are a lot of similarities with the Google stack. I mean, MapReduce, Google Process, and so on. There's also similarities with the Hadoop stack, right? Hadoop,
Yes.
Hadoop Process, pigs, and so on. I'm just wondering, is there some way to encapsulate what are the key differences? So I can sort of.
So what are the differences between the various stacks? And
Highlights. How would you separate them?
And I only know about the Google stack when I read a paper, okay? And that's fair. And they've written more papers than we have, so I'm by no means, pointing fingers and complaining. I like what we're doing in the PubSub stuff better. I think the event processing is better than triggers, and I think that's mostly a software engineering argument. There's a lot of similarities. There really are. I think I know in our store layer, it was fun reading the discussion in the communications of the ACM about the reordering of the replicas that occurred when you have multi-writers against that. And then I had an epiphany as I was understanding that. The chunks are fixed size in GFS. And so because it's a fixed size chunk, if the primary keels over, you have to get a new primary on the same chunk. Okay? And then that leads to occasionally the different replicas having different contents, which fascinated the hell out of me. Because we don't do that, right? We just truncate the extent. We have shorter extents. Right? And so we never have that anomaly even under multi-writer. We go through this, oh my God, it's a failure, what are we going to do? Oh shit, how long is it? And we figure it out, and it works great, right? But a consequence is that the stream structure now has variable length extents to deal with, which is more of a pain in the tush, but it's not the end of the world. So but these are nuances. I mean, they're great discussions, but I'm not going to tell you that, and I think though, by the way, structured streams is different, in that we have a more deep understanding of the layout. From what I understand, and it could be that I'm ignorant, the fact that we deeply understand in the compiler, in the language, and in the placement and the indexing, I think that makes for and that's built into the execution engine and the compiler, I think we're able to get performance advantages out of that.
That's reminiscent of pig, right, where they can sort of go into the file and extract fields.
I believe you. I will believe you. I haven't done all the reading on pig, so I'm not going to argue with you. Okay? But we're doing great stuff, and we have a great and worthy competitor, and so I have a lot of respect, and so I'm not. There's no denigration there. I mean, it's fun going to work. Yes.
Have you explored the suitability of column architecture, column store architecture for the kind of processing you're doing with something?
So. It is interesting. The question is, have we explored the suitability of column store architectures? So when I talked about the fact that you might put out a stream and put out 20 columns into one stream, it turns out that there's a great deal of control in the scope developer and say, no, I don't want to do 20 columns. I want to do 2 streams with 2 columns and 18 columns. Okay. Now, why do I do that? Because I'm processing this a lot without that. That ends up optimizing your ability to do rapid processing sequentially through that. So that ends up being a column-oriented store. So it's the trick with relational is everything's supposed to be hidden, okay? And that works when you've got one computer or something that is pretending to be one computer, right? When you're talking about these data set artifacts like this, it becomes different. The thing I'm fascinated with on the tables is that it's a blurring of those two, right, as to whether it's 1 or 2. And so we're going really hard to make sure that the perception of a table is a programmatic abstraction, and underneath we may break it into multiple tables, but that would be to penalize random, because I got to do 2 reads to put it together, to optimize sequential. And so it's very much in the same genre, but twisted differently. So your question's very meaningful. It's just, you have to stand and put your head sideways to get it differently. Okay? One more question. And then, how am I doing on time, Reggie? Okay, yes?
Just a brief question. Are there any plans to write papers or reports on Cosmos?
Well, I have a paper on structured streams that's not quite done, but it's almost there. And so.
I'm following up on Hector. I mean, I guess when we teach these things, these systems in the class, we have to.
No, I totally get it. And
so that's I think is the intent of Hector's question.
Right. The point is, Microsoft, you jerks, you have not communicated effectively. Okay. And I'm not going. No. I'm saying that.
When it comes to reading papers in Cider.
I'm going to say that, okay? Well, I actually sent a structured streams paper to Cider, but they didn't like it. So there you go, because it was like a database conference. And they said, this is old shit. So, okay, fine. So I haven't figured out the next place to send it to. I'll send it to you guys, right? But it's like, but so we will be communicating this more because we realize it's the only good way to get talent to come in. We had one recruit call us up and say, "Nah, we're not going to come and see you because we want to work on big data, and I'm going to go work at a Hadoop company." It's like, "Oh, okay, bye." Yes.
Two questions, Pat. One, what is the utilization of your clusters? Not 100%. What are the bottlenecks? What are some of the open research questions?
So, what is the utilization? What are the bottlenecks? What are some of the open research questions? Oh my God, the whole question. First of all, we're mostly CPU bound. I mean, we're always trying to be the CPUs are the big precious resource, and we're not having too much trouble with the IOs right now. And so, but that's also because most our computation is ginormous IOs and sequential processing, and so you get the thing off disk, and now it takes some time to crunch through it, right? We have huge challenges with predictability of the answer coming out, right? Because we're trying to place things with locality. You have outliers. How do you manage the outliers? There's some really great assistance we're getting out of MSR in looking at different approaches to that. There's wonderful ways that these things could be done in a great research area. That's a huge area. I mean, I don't even know that I can enumerate all the areas of challenge. Am I answering your question? Okay.
And what's the overhead on the compression? So roughly what fraction of your CPU is spent on the compression, decompression?
And I don't know the overhead on compression and decompression. I do know that during the batch job itself, we are much more, we do a medium job of compressing, and then we write it out durably. And then during that scrubbing process, when things are a little more idle on an extent node, he'll pick something up and say, oh, I can do better, and I'm not a compression expert, but I know that they're then using algorithms that are very compute intensive to create the compressed value, but not that bad to decompress, and then writing it back and then salvaging some stuff. I know that it was funnier than hell. We were like running out of disk at a year and a half ago or something. All hell was breaking loose, and the guys who are managing the directory are like up all night, and it was just awful, and there's just stress, and the whole team's like this because we're running out of disk and everything. And the dev manager, my buddy, he makes a call that we'll release Express 9 like a week before we were going to because the tests have been really good and it looks really good and we're running Express 8. So we just released that and it starts working its way through the thousands and thousands of machines and hitting the extent node. And the extent node is doing his scrubbing and now he's writing it back much squishier, right? And all of a sudden the total fullness of the cluster is going, and all the guys who are responsible for pounding people into deleting data, like, oh, It's just fascinating seeing a living, breathing system. And so compression is a huge trade-off in terms of storage versus computation. Mm-hmm. That make sense? Yeah. Thank you.
Okay, so I would like to start where Pat left. So in science, money is in combining basically lots of different kinds of data. And so I'd like to talk about the journey over the last 10, 15 years where we went from basically terabytes to petabytes. And so in the science of big data, the data is growing exponentially, and it changes the nature of science. And we know this, but now we see it happening right in front of our eyes. And what is most important about this, that this is a non-incremental process. So it's not just adding 10% more CPUs or 20% more CPUs, et cetera. we need to do things differently. And it's, again, not just science by itself, but it's industry and government faces the same kind of challenges. And what we see also is an interesting other process that physical sciences have been traditionally more dealing with computations and data, and now this is coming in a big way into life sciences, and not just in genomics and systems biology. So basically in every aspect of life sciences. And also simulations are becoming a much bigger part of the picture. And people are even are now simulating, the whole country at the level of the individuals, so basically the behavior of people. And so we see what is amazing about this, that we see a totally new scientific revolution happening right in front of our eyes. And this doesn't happen all that often, in the history of science. And we are living through one right now. And so science is moving. One of the most profound non-incremental changes is that science is moving from hypothesis-driven science to data-driven science. And that's, again, this sudden change is the most obvious in the life sciences. But it turns out, I always wondered why was it that astronomy has jumped on this bandwagon much faster than everybody else, until I really realized that this is the key, that astronomy has been for centuries basically data-driven. So when people looked up on the sky and they saw the fuzzy objects and we realized that those are galaxies, we didn't start out with a hypothesis that there are galaxies and they should appear the following. Or when people spotted the first supernovae, just something went ping on the sky. And so we didn't have to undergo such a big mental change to embrace this new way of doing science, and having access to just a lot more data was quite natural and a very happy day for most astronomers. The challenges are really very multifaceted. So it is not just that we need a little bit more storage, we need a little bit more computing. We really need new architectures with a different balance between CPU and I/O. We need different algorithms. When we have petabytes, there's no way that we can do, for example, an n-squared algorithms over all the data points, or we can really run a perfect query even over a 100 petabyte data set where we return every row that is needed, or we use every row to compute an aggregate. And we need altogether new kinds of computational tools and strategies, and it is not just statistics. So it's not just that we can talk to statistics and then the statisticians pull out the new algorithms out of the hat. It has to be also computable. In finite time, it has to have the right scaling properties. But it's also not just computer science. It's not just computational science. It's not just astronomy. And this also represents a challenge for the kind of people we need to train for this next generation. So when I was on the UK Science Review, about 2 years ago, somebody in one of the town hall meetings said that today's people are T-shaped in science. So they are deep in one area, and then they have a broad and superficial knowledge across many. And he said that we need pie-shaped people who are equally at home in their own field and at least in one of statistics or computer science. And so the challenge is that how do we take today's higher education, which trains people to be deeper and narrower every year, basically to be equally at home in these computational techniques in big data. And in many ways, I see an analogy to the time when Leeuwenhoek built his first microscope. It looked like this. And he looks through it, and a whole new world opened up. And in science, when we basically provide a tool that most scientists can look through, so a microscope of data, that we can look through petabytes of data that are available, then we will see a similar kind of revolution. So what is scientific data analysis today? What's the landscape? So basically, the data is roughly doubling every year in most areas of science. In genomics, it's growing much faster, and typically, or medical imaging. Architectures are increasingly CPU-heavy and I/O poor, so we need new architectures. We found over the years that databases are a good starting point because they can do sort of the very quick data extraction queries and the aggregations equally well. But there is an issue, it's clearly there is an issue with the scalability. So loading a petabyte, ingesting a petabyte into a relational database is a major challenge. So we are bleeding when we are trying to do this. So, and also we need, so scientific computation, I get into this, it's diversifying on the edges. So we need to be able to talk to GPUs. We need to be able to represent structured arrays. So Mike Stonebreaker is building SciDB, which is an array. The arrays are the primitive data structures there, and so on. We need, again, I can't emphasize how much more we need incremental and randomized algorithms, quote unquote. We need streams, basically. We need to stream through the data. Okay. When we look at how most of the scientific data analysis is done, it's typically done on mid-sized Beowulf clusters today, which are put into broom closets. Okay, the physics building at Hopkins had an electric meltdown about 1.5 years ago. It took us about 4 months to recover from it, so we are basically going beyond, so we are just using up too much power. And we are already at the edge, so this cannot go on much longer. Every new incoming faculty wants his or her own cluster. So basically, it's totally balkanized, and it cannot really be sustained. So the question is, how are we going to do this brave new data-intensive science, basically, in this world? And so I had the privilege to work with Jim for many years, and he codified a lot of the things that we need to do. First of all, so he really pointed out that scientific computing is revolving around data. Okay, we need a scale-out solution, so we will not build sort of a data supercomputer in a single monolithic machine, like the craze used to be. We need to take the analysis to the data. Today, it seems so natural. Okay, so that you know, we take all the analysis. That's what the cloud is about. But it was not so clear 15 years ago. He figured out a way how to talk to scientists, so we first met, he said, okay, give me your 20 queries about what you want to ask from the data. And I said, okay, so I want to ask anything and everything from my data. And it takes a while for scientists to realize that not every question they want to ask is equally important. We have to prioritize, basically, what we want to get out. And also the going from working to working. So in typical big science projects today still start out with a 100-page requirements document that takes many years to basically write and then another 5 years to implement. And during this time, we have gone from Corba to the computational grid to web services, to grid services, now the cloud. So every 2 years, there was a different distributed computing paradigm. You go into a 7-year development process. If you don't look up in the middle, then it will be a whole different world by the time you finish. And so Jim said, okay, let's just hack it. And let's build something that works today. And the only thing that is certain that in 2 years, the world will be different. So we have to write code in such a way that it will also work 2 years from now. And so we all contributed. I think many people in this room contributed to this wonderful book. So we set out with Jim it was actually more like 15 years ago, really, to build scientific databases. And it started all with the Sloan Digital Sky Survey. And about halfway into that project, we saw that, okay, that problem is solved by and large. And so let's see what have we learned and what are the lessons learned for the rest of the sciences. So we started to expand other sciences, environmental sensing, and then into medical databases. And we were exploring what can be transferred. And what was one of the most generic patterns that we were able, due to the nice CLR integration and SQL Server, we were able to put quite a lot of science code into the database. So for example, in the Sky Server that we built, we have currently, I think, several hundred user-defined functions that users can execute, which captures from curved space-time, et cetera, quite a lot of complex astronomy. During this time, the data sets grew from 100 gigabytes to 1 petabyte. And it's obvious that there are interactions with every step of the scientific process. You know, so Sloan built its own telescope. It started in '92, finished in 2008. And originally, we set out to image about 2.5 trillion pixels of the sky. We ended up doing about 5 trillion. By the way, the project was supposed to finish in about 8 years, so around 2000. So it took twice as long. Cost about 4 times as much. But so we set out to take about 10 terabytes of raw data, and we thought, okay, maybe we archive one more copy. In the end, we had many different versions. We had to archive 120 terabytes. And we saw that the database will be half a terabyte. It is now, today it is about 35. But had we finished on time, none of this would have been done because we could not have afforded to store this much data. So in a sense, Moore's law and Kreider's law came to the rescue. So the fact that we took twice as long, the technology has evolved so much so that what looked like very difficult challenges in '92 became almost trivial, basically, in 2008 by the end of the project. So that was one of the big lessons. Don't rush these things. So this is just a three-dimensional map of the sky. This is just cutting through. And the Milky Way is here. So the plane of the Milky Way where we can't see through the dust, but you can see all this nice frothy structure in the universe. And this shows how this, of course, after Sloan, the surveys haven't stopped. So PenSTARS is underway right now, which is collecting in Hawaii about 1 petabyte of imaging data per year. And by the end of the decade, LSST is going to go online with about 10 petabytes a year of data taken. And this figure is coming from Tony Tyson. So the green line is the aggregate telescope area by all of astronomy. The yellow is Moore's law. Okay, so the number of transistors per CPU, and this is the number of galaxies detected on the sky. You can see the two are not decoupled from one another because the CCDs that are used for this imaging and the computers that are used to processing are all basically based on Moore's law technology. So this technology is driving basically the explosion of data. However, it's a good question to ask that how long does this trend continue, this doubling of data? And if I ask the same question about particle physics, is your data doubling? The answer is no. We built the LHC, which cost of the order of, I don't know, short of $10 billion. And there, the detectors themselves are multi-billion-dollar instruments. So when a new generation of CCD detectors or new silicon detectors come in, we are not going to throw out the old detectors. So we turn on the LHC, and it's generating data at a fixed rate. So the data volume at the high end for the most expensive project in the world is always going to be linear. So the exponential is coming from the fact that I'm throwing away my digital camera every 2 years, roughly, and my laptop probably every 3 years because of the technology evolution. So at a fixed cost, one can buy exponentially better devices, basically, until this technology trend continues. So we can ask that how many generations of instruments are there left? And are there new growth areas emerging? And it's obvious, the gene chips have caused a similar revolution and the sequencing, basically, in genomics. But what we see now also that software is becoming a new kind of instrument in its own right. And there are the value-added data, which is the federation of different data sets. We have hierarchical data replication, so basically creating from the very big archive, create some local copies of smaller and smaller data sets. But the most important thing that's emerging now is the large and complex numerical simulations. So with the CPUs, it's becoming increasingly easy to generate large simulations. And they have gone from, in cosmology, in astronomy, from a few million particles about 10 to 12 years ago. Now we are at the level of trillion particles in a simulation. But there is a problem. These simulations are typically run on the world's largest supercomputers. At these supercomputers, there is a smaller and smaller fraction of people who can access these. And as the data sets are becoming larger and larger, they are unmovable. You cannot move them, so there is smaller and smaller fraction of the community who can really access these simulations, why actually the whole community would like to compare them to observations. So there's a stress there. And how do you, first of all, interface to a very large simulation? And so one of the interesting toy models or examples on this is a turbulence simulation that we have been playing with at Hopkins. This is not very large yet. Much bigger ones are on the way. So here, This is a 30 terabyte data set. It's a 1,000 cube box with 2,000 time steps. And normally, this was run over and over again on the Beowulf cluster, and basically, some test particles were inserted and the trajectory followed, and people did statistics on them. And they could never get right where to place the particles because of the chaotic nature of the flow. So they basically always ended up in the wrong place in the end. And this was not converging. So the idea came, why don't we try to store this whole thing on disk every time step, and then build a very good spatial index so that we can extract little infinitesimal volumes. And how do we interface with this? The typical way is to download all the raw files of the simulations, all the big arrays in HDF5 or whatever, and then access it. But when it gets to 30 terabytes or 100 terabytes or a petabyte, this is not feasible anymore. So we came up with a paradigm that why don't we shoot test particles from a laptop using a SOAP web service into the simulation, and they are like virtual sensors, like in the Twister movie, and they report back the fluid velocity or pressure or the dissipation rate, and basically then send back these reports to the users. And this worked like a charm. So this is the typical daily load. So we deliver on a good day about 100 million particles to the community, where people from all over the world are shooting these particles in from their laptops. And these are papers, so some of the most prestigious physics journals have been using this facility now for several years to generate world-class papers. So, and now just recently, after trying it 4 times, we finally got funded by the NSF to do the same thing in astronomy. So take a simulation that will be run at Oak Ridge. The raw simulation output will be about 2.6 petabytes. And we would, once we compress and pack in the database, it will be about 800 terabytes. And the idea, again, that users can insert dwarf galaxies which collide with the Milky Way and get disrupted. And we have seen about 15 such events already in real data. This is a picture taken by an amateur, and you can see a dwarf galaxy coming in, and as it collided with the plane of this Milky Way-like galaxy, it left a trail of stars behind, and you can see the orbit, actually, on this actual image taken by an amateur. Why using a database here? So it turns out that we need a very fine-grained, very accurate, and fast spatial index. Databases are very good at using B-trees for B-tree fetches. And with Jim, we came up with a nice paradigm. Again, how can one create basically a hashing function, some sort of a space-filling curve, and map it essentially onto a B-tree index of a database. And we don't have to build then essentially our own spatial index. It's given for free. The price is that we have to load the data into the database. So anyway, so this project is now underway. And this will be a numerical laboratory where users can perform real-time experiments basically on a petabyte of data. How do we visualize? So if we build such a laboratory, it would be nice to see real-time interactions. And again, the traditional way of doing visualizations is these days to buy a really expensive high-end GPU, okay, and then essentially copy the data into the GPU and then do all sorts of processing on it. But when the data starts to be large enough, then the data stream is becoming the limiting factor. At the same time, we should realize where the world is heading, that every device pretty soon in the world will be capable of receiving a 3D high-definition video stream, basically. So that bandwidth will be available to everyone, and bandwidth beyond that will be probably premium, so it will be very expensive. So I think it's a logical thing to think through that in this world, if the data is too large to move to the visualization device, we should move the viz device to the data, do the rendering on top of the data, and basically have the users control, so capture the user actions, and then have the data, have the visualization stream basically to the user, so put in a codec and then basically put it on an iPad. And so we have been trying to do this with the turbulence simulation. This is actually a cosmology visualization that was on top of 1 terabyte of data. where again the data was on the same machine as the GPU. This was done by my son when he was an undergrad. He had an internship, and he built a clever octet structure which basically enabled him to do a very good rendering, but doing a very efficient data streaming. This is the turbulation data streaming from the database directly into the Viz engine. So we put a GPU card into the database server. This is the vorticity, the vorticity lines, basically. So it's quite beautiful. Anyway, let me just show basically 2 videos. So this is done by Kai Bürger from TUM in Munich, who works with Rüdiger Westermann, and we are collaborating on this. So this is displaying the evolution of the, so he's putting in, so he's streaming in the velocity field from the database, computing the vorticity vector on the fly, and then inserting lots of test particles then which move along then the vorticity field. And these are basically the fixed points of the vorticity field. And the next picture shows just 3 layers of 24 million particles each. Okay, and how they move again in the velocity field. But the beauty of this is that this is sort of 6 gigabytes per time step streaming from the database directly into the Viz engine in real time. Okay. So this is, so this was kind of the science motivation. And let me go to the next page. So we have spent some time over the last few years in extending databases further. So not just the CLR integration, so and putting various class libraries into the database, but how can we integrate, for example, GPUs into the database world? And it turned out this turned out to be easier said than done. When we set out, we didn't quite know what we are getting into. So there are all sorts of, so there's the Windows scheduler and there's the SQL Server scheduler. And so it turned out we couldn't launch a CUDA thread from SQL Server. It had to be under the operating system control. So the only way to do this legally was to have an IP, so to have a memory resident Windows service, which is communicating through IPC. So we send a query string to this application, to this service, and then it pulls the data into a buffer from SQL Server, executing it, and then passes the handle of the data to the CUDA, to the graphics card. But we were able to essentially write user-defined functions in C#, where the kernel of the function executes in CUDA on the function in a really seamless way. And we did some interesting science with it. So in the Sloan map that I showed you, you saw this little sort of fuzzy structure. It turns out this is a correlation function of the galaxies from the same map. And anyway, what we see here is kind of a bump. This bump is the resonance frequency of the universe when the universe was about 300,000 years old. It behaved like an acoustic drum. And we were able to detect this, but in order to do this, we had to compute 600 trillion galaxy pairs. This was done in SQL Server. Okay, so this is already, it just as a computational task, this is not trivial. So I spent about 10 years on writing optimal correlation function code, which instead of n squared, they were n log n algorithms, so together with Andy Connolly at UW. Okay, and in come the GPUs. It turns out it was much easier to run 100,000 threads of elementary n squared process than trying to traverse through trees on a SIMD machine, because then because of the tree traversals and the conditional instructions, essentially it all fell apart. The parallelism was lost. So we are learning to rethink some of the very fundamental knee-jerk reactions in algorithms also with these. Anyway. The other thing that is emerging with the simulations, that a lot of the data in the large simulation is coming in regularly gridded arrays, structured arrays. And so we see the need in our everyday use, basically, to use large arrays in databases. This is, again, the motivation why Mike Stonebreaker has completely started out with arrays as the primitive data types inside DB. But in any case, we have been working with Jose and Dragan Tomic in Belgrade, Microsoft Belgrade, to build an array library, and Laszlo was an intern at SQL Server last year here in Redmond. So we built basically, or he built really an array library, a primitive array data type for SQL Server, which is a multidimensional array, but it has all sorts of MATLAB type functionalities. So we can take subsets, we can slice and dice and aggregate things. So using just plain SQL Server commands, which sometimes are a little bit more awkward because we don't have access to the parser right now. So we had to just use the user-defined function syntax to wrap this, but it works like a charm. So, and the third technology project I'd like to mention is the thesis of one of my students who has been an intern with Roger a few years ago. And basically, this has a lot of similar features, I think, that Pat and Roger are working on, except that, we had to have something that works now. So this is sort of the duct tape thing that we need to use these features today. So we would like to add a layer to an existing RDBMS, to SQL Server, that supports, for example, statistical queries. When you have multiple petabytes, the notion of getting a perfect result set is really not very meaningful, because sometimes we couldn't even store or look at the result set. What we want is to have some aggregations where we can also guess the result of the aggregation early enough, but when the answer is already good enough. Anyway, and we have to have fault tolerance, scalable behavior. And so it has a MapReduce-like crawler behavior, crawling over a very large database, where the database is sliced and diced into little pieces. And so the idea is to break up the data into small partitions and tiles, and then intercept and rewrite SQL, and then farm out customized SQL to each of the tiles. And then we run a query stream on the tile set. And then, but we don't have to execute necessarily the streaming order sequentially, but we can actually pick and choose if we have a good random sample of the database. So we can go to those, so we can beat the square root of n central limit theorem scaling or convergence a little bit if we are smart. And so the idea is that the TileDB can adapt a little. So if the data layout is, for example, not optimal for parallelism, it can always nudge. Every time we execute the same query, it nudges the data a little bit farther, closer to optimal layout. And also, if a machine is slow or failing, then essentially it gets knocked out of the queue. And this was done by a single graduate student over a span of 1.5 years. So it cannot be really compared to the enterprise efforts here. But Nolan is one of the smartest kids I have known. And this is roughly, how it works. So last bit. So I sent out a survey about 1 year ago to some of my colleagues who were working on large simulations, that what was the size of the data sets that they generated in the big simulations and data processing, how many computer cycles, CPU cycles they used for this data set, and what was the limiting factor. And I was expecting that what comes out is that the high-end machines don't have fast enough sequential I/O to store the data sets. It turned out that the higher-end machine they were using, the smaller fraction they were using even of the slow I/O. But what was constant is the size of the data set. It was always between 10 and 100 terabytes. So basically, everybody in science today gets stuck between 10 and 100 terabytes, because 10 is easy, and 100 is basically the choke point. And so, and 300 is really hard. And basically, 100 terabytes is when you start to have to build a system. You cannot use a single, just hooking up a bunch of this to a single workstation. And also, if we have a large enough data set, we have to realize that if the access is not sequential, we simply cannot really do it, if we have to rattle through the regular hard disks over 100 terabyte data sets. I also came across that 100 terabyte is hard for another reason. How do I move 100 terabyte even within the university, from the medical school to physics? And the answer is basically you drive. So I had to copy basically disks over at the medical school and drive over the disk to the other side of town. So the Hopkins backbone today is 10 gigabits. And if I took it over for a day, then I could have copied the 100 terabytes. But the problem is that also to the server rooms, we didn't have a 10 gig connection. That was only between basically the routers. So as a result, Hopkins is now trying to set up a 40 gig just data-only network between 6 locations on campus which have sort of bigger data sets. So we are trying to work, off this step by step.
Wouldn't it be cheaper to get students to drive?
Yeah. Well, that's what we do today. But also this brings up the issue, so even if there was a fantastic location off campus, how do we move even a 100 terabyte data set, not to mention a petabyte over there? Yeah.
These data sets of 100 terabytes and up, petabytes all the way to exabytes, aren't born instantaneously. They're born a gigabyte at a time, more or less, inside a simulation or inside an observation from a Skype.
Yeah.
If we would only plan ahead, that's one of the things the LHC has done. They're sort of incrementally moving the data all the time around the world. And I think the rest of science needs to start doing this. Otherwise,
but they also have several dedicated lambdas across the ocean.
They do. But they also have places to put the data. And
sure. And that's exactly right. So how do we go about this, and what are the trade-offs in science that we need? So there was a really good talk by Stu Feldman at Szalay, where I think Leah Burton was there, I think, at this meeting. He talked about extreme computing that is about trade-offs. And I realized there and then that there is actually a difference between scientific computing in its trade-offs than the typical commercial cloud computing. So you simply have to focus. The business is different. And so I tried to write down my criteria for this. So first of all, what I think the most important is total storage. And this means that we can't afford to store 6, 7 copies of data. We have to live with 3 copies typically, or 2. The cost is then very relevant, that over the price of the raw disks, how much does the whole system cost? So that when we include everything, then how much sequential I/O can I get? Then once I kind of scan through the data and start to get into the correlation business, the n-squared algorithms and so on, then we need basically a fast way to process the incoming data streams. And then we also do need to do this at a moderate or low power. So how do we build a petabyte? Or what is the price of a petabyte? This is actually a little dated. So this chart is from Backblaze. So in 2009, the price of a petabyte of raw disk drives was $80,000. The Backblaze chassis, which were homegrown, if you put this into this homegrown chassis, it was about $117K. If you buy the same thing from Dell, it was $826. From Sun, using the Thumpers, it was $1 million. Amazon Cloud for 3 years was $2.8 million. EMC squared was $2.8 million. This price is for over 3 years. And this is the low redundancy storage, not the high redundancy storage, Amazon. And I think Azure would be similar. So basically, in 2000, we filled up a whole lab of these disks donated by Intel. These were we built a terabyte out of 20 gig disks, and this filled the lab. So in around 2008, we built a Grey Wolf, which was a 1 petabyte cluster built out of Dell equipment. We paid the $800K. So in 2008, the price was the same. It turns out this looks like an enormous, a factor of 1,000 over almost 10 years, but it's actually 2 to the 10th is the number. So we were probably a little bit ahead of the curve. So in 2000, we were really starving. In 2008, we had some empty space on the server. Today, it's maxed out. So we are already filled up. So we are on the curve. And so last year, I put in a proposal to the NSF to build a new instrument. Incidentally, I called it Datascope. I didn't know about Roger's project. But I have a hyphen in the name. So the goal was to build, so see what we can build from about $1 million. Okay, if we do it on our own. And the idea is one lesson we learned on the Grey Wolf, that it was not good, not all data is equal. So we need also some places where we can park the data, which is slower and higher density, and also a performance tier where we do the analysis, where we can go all out. Anyway, the bottom line is that we think we can build about 5 petabytes plus at a sequential throughput of about 0.5 terabyte a second for the analysis layer. And if we fill in some of the machines with GPUs, we can also put in about of the order of 200 teraflops. I think this was a slight overestimate. I don't think we can afford 270, but we can probably afford 200. Anyway, so this will, we are over the next few months, we are actually putting these things into the machine room. But what is most interesting, I sent out a proposal or a call for proposals within Hopkins. Who has big data that you cannot analyze today? And how much is it? And write me a half-a-page mini proposal. There were 19 projects who came in. This is the total aggregate data size just within a single university, 3 petabytes today. This is the distribution of the data set sizes. You can see that it kind of peaks around 80 terabytes today. That was actually last year. And I think this curve is shifting up every year. And the last bit I want to talk about is what I see is an increased diversification. So basically, the different groups try to diversify, and we have all sorts of evolutionary pressures, but nobody wants quite the same thing. So large floating point calculations increasingly migrate to GPU clusters. Big data moves into some cloud-like storage, whether it's private or public, and what's the business model is a detail. But data is aggregating naturally. Random I/O is increasingly moving to solid-state drives. Stream processing is becoming increasingly important, and also in terms of software, we see a much wider, much bigger diversity than we have seen in the past. So from old NoSQLs, databases, column stores, IDB. So at the same time, what remains then in the middle if everybody diversifies? It's the data. So it looks like everybody has the same problems in storing the big amounts of data. So basically, we see diversity on the surface, on the computational surface. But deep down, everybody basically wants to store hundreds of terabytes and keep it there and accessing it and generating new data. Boutique systems are dead and commodity rules. So all the pieces, the SSDs, and nobody can afford an enterprise, even an enterprise hard drive. And we are still building our own because all the other value propositions are just so off scale of the science budgets that I would rather spend my own time and my graduate students' time to build a system than buy something for 10 or 20 times the cost. So summarizing, science is increasingly driven by large data sets, which are here, but we don't have any cheap off-the-shelf solutions that we can just take a recipe and run with it, like the Beowulf was. We need a new instrument, sort of a microscope and telescope of data. We see the increasing diversification over commodity hardware. We see a huge change in sociology. Most of the data collection now in the big data arena, at least, is happening in large collaborations, but the analysis is not. Analysis is done by individuals of the public data sets. And we see a new force paradigm of science is emerging, and which is not incremental. And I would like to finish with a Henry Ford quote, which I think is very appropriate. So when you ask a typical scientist, what do they want? They would say they want faster computers. But we know that we have to do more than that. Thank you. Just shout.
All right, so one of the data challenges that I didn't see in your talk was data integration, which is particularly huge in environmental geoscience kinds of applications.
Yeah.
Because most of this seemed to be about just a single giant data source. What do you see happening in that arena?
It is just as big a problem as the big data set itself. And so basically data sets and the computational changes are probably a 1/f power law. So here we have a problem on the far end. And what actually almost all scientists want to do, they have their own little data sets, and they want to actually join these with each other plus the big data sets as well. So they want to do all of this. And this is not an easy thing to do. The other federation challenge is that a lot of the data sets are still not stored in the same location, so they are geographically isolated, and there is a network in between. So we need to do clever heuristics probably to overcome until we will live in a world when there is unlimited network bandwidth. So, but yes, it is just 40 minutes. So yeah, Kenji. Yeah.
So a couple of slightly loaded questions. What's your view on how the cloud will play a role here, not currently but in the future? And is the challenge technical or business model?
I think both. But so I think, okay, so the business challenge is if the cloud storage, first of all, and moving data into the cloud was 20 times cheaper, people would migrate like crazy. So it's just a question of having the right price. And then the technical part is that also then having the right computational characteristics and the ability to diversify. You can see already Amazon offering, for example, GPU instances and so on. So I think where I see, for example, all the data scope and all the things that we are trying to build in Hopkins as like the prototypes, what, for example, the Azure nodes could be like in 2 years from now and so on. So where one could build some nodes which max out the I/O, and one could build other nodes which are the big memory nodes and some random access nodes. So put some diversity actually into the system so you can migrate the relevant applications to the right place. But the economy of scale is an argument that is hard to beat. So.
What do you see, as follows on a question of integration and federation, what do you see as the challenges of integrating or federating legacy hardware and software?
Probably have probably emulators. So I mean, okay, so there is a big trend now. People are playing Commodore C64 games on emulators. And I guess there will be then Sun emulators where people emulate the Sun run an emulator of an old Sun workstation. It will be easier than porting the code. So probably using this on virtual machines, of course.
We'll take our speaker one last time.